Okay, so this is the first problem we're going to work as a class. We're going to construct the shear force and bending moment diagram. Without getting into the details first of how to do that, we always want to find our support reactions first. So I'm going to slide over here to the side, different than what I normally do, and I'm going to draw a free body diagram of my beam. But I'm going to pay attention to using shear force and bending moment sign convention. So when I'm looking at the reaction here at A, which is a force in the vertical direction, I'm going to come over here and assume that it's going to be the shear force at A, and that's positive shear force acting up on the left-hand side. And when I go here to B, where we have, again, a vertical support, I'm going to draw that as positive shear force at B. That's what positive shear force is on the right-hand side. It's down. Everybody see that? It's a pin, so there's no moment, so I don't have to worry about moment. And over here there's a roller. Both of these are external, so again, no moment. So those are the only two reactions I need to a system that has a load P and another load P, and they're at distances of, looks like 3L, they're each at L. Everybody see that? Since I'm going to draw a diagram of shear force, I want to put my positive conventions for shear force there. So how do I find those? Well, I'll sum moments. And I'll sum moments, I don't know about which point. I think I'll sum moments about B. And I'm going to do that. I should be able to find my shear at A. So about B, both my loads are creating what kind of moment? About B. It's like positive. And my shear at A is going to create negative moment. So I'll have a negative moment for the shear force at A. The distance is 3L. Then I'll have positive moments of a force P, distance L, and then again P with a distance 2L. So when I solve for my shear at A, I get P. Not surprising. But because I assume positive shear force, I know the shear force at A is positive P. Okay, nothing to that, right? So now if I sum forces in the y direction, I have the shear force acting up. That shear force is down. What kind of force is that? That's negative. That's acting down. And then I've got minus P, minus P. So when I solve for the shear at B, what do I get? I get minus P. So what is the shear force at B? Minus P. So now what I like to do is draw a little template. There's the beginning of my beam. There's the end of my beam. Then I'll come and I'll establish my positive x-axis. I'll also say this is going to be positive shear. And normally I'd put some unit there. Today I'll just say, well, that's going to be some force. I don't have really units on this problem, but that would be my force unit. So you don't have to necessarily, every number on your diagram, you don't have to put a unit next to it. If you just indicate what the units are of your force. Kips, kilonewtons, whatever. Okay, so what's the shear at point A? I found it. It is P. So I'm going to start at P. What's the shear at B? I solved for it. It's what? Minus P. So I'm going to come and mark that minus P. So I know where I'm starting. I know where I'm going to end. If I can't connect those dots, the next thing I do, then something's not right. Okay. Now, what else is going on? Well, I also know from our previous discussion that as I go from the left side and past this point moving to the right, I'm doing it twice, something's going to happen there. What's going to happen? Yeah. You might remember that the change in shear was equal to the load. So those are pretty important points. So I'm going to add those points to my template. Another way to think about it is indicating regions where your load is continuous. You'll notice here that I have a continuous load. What is the loading here over L? It's 0, but it's continuously 0. And then there's some abrupt change, and then it's continuously 0 again. And there's some abrupt change, and again continues. So that's why I've denoted these 3 different regions. Now, you might remember the math I had, that I know that the change in shear is equal to the area under the load diagram. Right? So let's apply that. Here, I'm starting at what value of shear? P. And I want to look at the change in shear over the first length L. So I go up and I look at the area under the load curve in the first length L. What is the area of the load curve? There is no area in the load curve. It's 0. So what's my change in shear? 0. So if I start at P and I don't change it, I should end at P. No change in shear. What is the shape of the shear diagram? Well, according to this, the slope of the shear diagram is equal to the load. Right? What's the value of the load here? It is 0. What kind of curve has 0 slope? A horizontal line. So I can connect these 2 points. And there's my shear variation from 0 to L. What is the shear anywhere between 0 and L? Positive P. Now, it's positive P on the left side. As I move to the right side, how much does my shear change? It changes the amount of the load. What is that load? It's minus P. So P minus P is 0. So just to the right, my shear is now 0. And I finish this section. Now I'm going to move to the next section. And I apply the same strategies. So now looking at the middle third of the beam, what's the load here? 0. So if I plug in 0 here and I take the area and there's nothing, I get nothing. So what's the change in shear? 0. So if I start at 0, I should end at 0. The slope of the curve between those 2 points is given by the load. And the load is 0. What kind of curve has a 0 slope? Horizontal one. Horizontal. No shear in the middle third. Now, here's a point load, so I go from the left side to the right side. My shear change is what? Equal to the load, so my shear is going to change how? Positive or negative? Negative. Equal to P. What's 0 minus P?
Negative.
Negative P. Now, here do we match these up? Let's see. Well, the change in shear should be the area in the load curve. The load curve between 2L and 3L is 0. No change. Negative P plus 0 is negative. Yes! I have found my way home. I started at P and I found a path to negative P. Now, there are infinite number of paths between those 2 points that you could draw. There's only one that is correct. This one. Alright? Just because you start at P and you're going to end at negative P and you just start drawing a squiggly line in between. Yeah, you just drew a diagram, but it's incorrect. Okay? But this should be help. So one last thing is, what's the slope of the curve? Equal to the load. The load is 0. So a curve with 0 slope. There you go. Done. You might recognize this. This is the same loading that we used in Civil 1112 for our reinforced concrete beams. It's called third point loading. So between the two load points, it generates no shear, but where's the maximum shear? In the ends. Remember where you had to deal with all that shear reinforcement in the ends? That's why. That's where the shear was maximum. And you also notice it's constant. It doesn't vary. Okay? So I feel pretty good about my shear diagram. Now I'm ready to draw my moment diagram. So I'll again establish a positive x-axis. Positive axis for moment. Usually units of moment are going to be force length. And now I'll put on what I know. Let's see. Starting on the left-hand side, do I know something about the bending moment? Well, it's a pin, so what's the bending moment?
0.
0. What do I know we're at the end? What's going on here at the end? Well, it's a pin again. What's the moment of the pin? 0. So I know I've got to start at 0, construct a diagram that should end back to 0. But now I have a different set of conditions, very similar, but now the change in moment is going to be the area under the shear diagram. And the slope of the moment diagram is going to be given by the shear. So using the same strategy we had before, let's look at the first section, 0 to L. And I want the area under the shear diagram. So I go up and I look at this section here. What's the area of that section? Well, it's a rectangle. It has a base of L and a height of P. So the change in moment is PL. And if I start at 0 moment and I add positive PL to it, I should get PL. And what is the slope of that? The slope of this curve, the moment curve, should be equal to the shear. And what's the shear everywhere between 0 and L? It's constant and it's positive. So here is a constant positive slope. In fact, it would have a slope of P to 1. Positive P. So again, 0 order curve, well basically 0, there's a first order curve, a 0 order curve constant, and then one with a slope. Alright, so let's go to the next section, the middle third. The change in moment is equal to the area of the shear diagram. What's the area of the shear diagram from 2L to 3 to L to 2L? 0. So PL plus 0 is PL. No change. And what's the slope of that line? What's equal to the shear? What's the value of the shear? 0. What kind of curve has 0 slope? Horizontal line. So now we get to the last third of the beam, 2L to 3L. Again, the change in moment there is the area of the shear diagram. What's the area of this part of the shear diagram? Well, it's rectangular again. And it has L times minus P, so minus PL. So what's PL plus a negative PL? 0! Yay! We made it home. And the shape of that curve? Well, it's given by the shear, and the shear is constant and negative. So here's a constant slope. However, it is negative. And there's your moment diagram. You also might remember from the freshman class that our maximum moment, the place we had to worry about bending, where the concrete would want to crack, was right in the middle. It's because it had the maximum moment. I didn't tell you that then, but now you know. Questions about that? We're going to work a lot more of these. And no matter what this is, I'm going to do these things every time. Over and over and over and over. and over and over and over. All right.